So as far as what we're doing with this is a huge document, I'll let you know. 159 questions on this. We're not, first of all, you're not going to need to go through all 159 of them whenever I post this. There's a number of these that is just straight up skip these questions. Don't worry about these at all. Some of them are repeats, not direct repeats, but the same type of question being asked. So if you feel like you get the idea, you can kind of skip through it and look for stuff that you're not exactly sure about. What I highly recommend you do is any question that we haven't done today, or even the ones that we do, if you answer it, there's not an answer key for this. So let's say you're looking at this one and you answer B, but you're not 100% sure that's right, put a star next to it. The answer is not B. I hope you guys can do that one. Okay. So I'm just going to I picked out a number of these that I think kind of cover the whole gamut of what we did this semester. And it does not cover everything, but I feel like I picked some that gives a pretty wide breadth of everything that we've done. So if you're looking through it tonight, you have questions, come in with a list of questions that you have tomorrow during class, and we can go over this even further and just help you out. The questions are not going to be exact duplicates of stuff you see on this. But this covers all the same kind of content that you're going to see. So it's my long way of saying, if you can do all this, you should be fine on the test tomorrow. There's going to be about 20 questions on the test. And remember, it only counts if you do better than your current grade, only if it brings your grade up. And lastly, there's not going to be any FRQs on the test. So having said all those things, if other questions come up, certainly feel free to ask. But let's just start going through this. We're going to start with question number 10. Don't need to say too much about this, except that it's asking for a cumulative relative frequency. So the cumulative relative frequency here is going to be looking at anyone who studied up to 4 hours. So 4 hours or fewer. These two added together, that's 80 right there. Out of the total, and we don't have the total, so we'll need to add that up. And when we do that, the total here is 130. So 80 out of 130 is your relative frequency, cumulative relative frequency, okay? And you guys, of course, could do that math on your own. Again, just jumping around a bit. If you want to come back to any of these questions, certainly ask questions along the way if I say something you didn't understand. But if you want to come back to any of these that we went over, we can do that. All right, I wanted to show this one because it's a back-to-back stem plot, or also called a stem and leaf. So remember that the stem is right here, right in the middle. And so a 5-7 represents 57 home runs. So the stem comes all the way up to 140. So the question is, which league had the team that hit the most home runs by midseason, and which league had the team with the fewest home runs? So it looks like in both of these, the American League had the fewest and the most. And the actual amount of home runs hit the most was 149. And remember, something like this would be 90, 91, 92, 95, and 99. So keep in mind how to read these stem plots. Okay, and the back-to-back doesn't change it too much, but it's worth looking at. So this is one I wanted to look at just to remind you how to do this in the calculator. So it gives us a set of data, and it asks us to find the sample standard deviation. We are not going to calculate this by hand, even though on your formula sheet it gives you the formula you need. That's really time consuming. Remember, we just let our calculator do this. So I'm going to put these data points in as a data set. So you can do it right there if you want, but I'm just going to my lists, putting these values in. It doesn't take too long. There's only 7 of them to put in. They're all integers. Once I've got them put in, I can go back to stat, over to calc, and then the very first option is one variable stats. I'll just pick that list. I actually didn't put mine in list 1, so. And it looks like the sample standard deviation is 4.32. You're looking for S sub X when you're doing this. And they're asking what's the closest integer, what's the closest value. So, I mean, it's going to be 4 right here. So remember, those one variable stats will give you what you need. If you scroll down in your one variable stats, that's where you get your 5-number summary, and we will talk about that. So I should also add as a caveat right here that there are certain problems in here that might seem like we're looking at new information, but you know, it is kind of built on stuff that we've already learned. So the questions that I'm going to put on the test tomorrow are going to be kind of the middle of the road type question, if you think of it that way. There's the really easy ones, there's the really difficult ones, and then there's kind of the middle of the road. And that's kind of where I'm going to be shooting. Go to each unit, pick out some of these like standard types questions and put those on. So if you're looking at some of them that are really, really, really challenging, I don't think you'll see the super challenging ones. Okay. This next one, we're looking at problem 26 down here, but we've got our data set up top. And you can't see, but this is the points per game for basketball players. This is back in like 1998, 1999. And these are the Celtics, the Bulls, and the Supersonics back when they existed. And it doesn't matter what the 3 teams are. It's Boston, Chicago, and Seattle. So what we're going to do is we want to create some box plots out of this data. And we can do that by just plugging the data in to 3 lists. So I'm not going to go through and actually do that right now. That'd be somewhat time consuming. But I could plug that data set into a list, get the 5-number summary, or once I've got that put into a list, I could go to stat plot. You have to hit second and y equals, and you've got 3 plots. And remember, when you go to this, you have the option of creating a dot plot using whatever list you want to. So wherever you put this data, you just select that list and it'll create a dot plot for you. If you create 3 plots from each of these 3 teams, you can figure out what the middle 50% of the data is. That's really your IQR, your interquartile range. So it's looking for which one is the greatest variation in the IQR. Now we do have something of a shortcut here. There's only 10 data points and they happen to all be listed in order. So 50% of the data falls above and below that line. So I know that my Q1 is here and Q1 would be that one. So these are my Q3s up top, my Q1s. So if you don't want to go through that trouble, you could just do the math yourself right here and figure out which one has the widest variability. That's an alternate way of doing it for something like this. But if these weren't in order, we couldn't do that, or at least we couldn't do it easily. Okay. Again, if you need to come back to these because something I said didn't make sense, just let me know. All right. So the question for this one is based on the data in the table, and we'll go back to that. What is the largest number of births in a month you could possibly have and still have a lower outlier? So we're looking for the lower fence. I'll just call it LF, the lower fence where we determine where outliers begin. And we're only worried about the lower outlier for this particular one, but we could find the upper one. And as a reminder, your lower fence is your Q1 minus 1.5 times the interquartile range. So if we want to start doing this, we need to plug these values in and figure out our 5-number summary. So first thing I'd want to do with this is put these numbers into a list. And I'll give you guys a little bit of time so you guys can do this at home there. Once you've done your one variable stats, you can kind of look at those numbers. I'm going to put them on the screen here. And if I did this right, we should all have the same numbers. It doesn't give us the IQR, but we're going to figure that out in just a second. Okay, so hopefully that jives with what you guys have. The interquartile range is just Q3 minus Q1. So that'll be 319.5 minus 294, and that is going to be 25.5. All right. So now if I go back to this, I'm trying to find the lower fence. Q1 is 294 minus 1.5 times 25.5 gives me my lower fence set at 255.75. And I'll pause for just a second in case anyone has questions on this, but hopefully you're remembering all this fun stuff. So now we can look at what is the largest number of births in a month you could possibly have and still call it a lower outlier. Well, 255.75 is the fence. So 255 is just outside of it. It is a lower outlier. Okay, so had to do quite a bit of work for that one, but I mean, the calculator did most of it, just a little bit time consuming. All right, the next one, we're gonna jump down quite a ways. And you can see I'm jumping over a lot of problems. So if any of these are ones that as you look at it tonight, you're confused on, then certainly come back to class with those and we'll look at it. All right, so they're asking in 55 right here to find, okay, we've got a normal distribution. Sorry, I thought there was a table we needed to see. Okay, so we've got a normal distribution with a mean and a standard deviation. A sample of 950 is drawn from the population. How many of these 950 will we expect to find between a certain range, 57 and 73? So this is not a sampling distribution question. It's basically saying, assuming that we got a random sample drawn from the population and is representative, how many of them should fall within 57 and 73? So we need to figure out what the z-scores are here. We want to figure out what percent out of the population falls between 57 and 73. So the z-score for my upper number here, we'll do the lower, 57 minus 65 divided by 4. And remember, it's just the mean and the standard deviation getting plugged into the z-score calculation. So that's -8 divided by 4, and that's just -2. So pretty straightforward on that one. The upper z-score is going to be 73 minus 65 divided by 4, which is 8 divided by 4, and that's 2. All right, I could do a normal CDF calculation going from -2 to 2 with the standardized normal model. But we know from the empirical rule that within 2 standard deviations of the mean, we should have 95% of the data. Now, it might not be exactly 95% when we do that calculation. It's going to be awfully close. In fact, I'll just do that for fun. It is 0.954. All right, so if you're really particular, you could say 0.954. But for this problem, 95% works well enough. Okay, so if I picked 950 people and it was a random representative sample, then I should have about 95% of these be in that range. So I'm going to go just do 950 times 0.95, which is 902.5. And we can see that 903 is the reasonable answer there. Okay. 58. All right, this is just a conceptual question about normal distributions. So all of them are true, except we're looking for the one that is false. The normal curve crosses the x-axis at z-scores above and below 3 and 3.0, or and -3, sorry, 3 and -3. Now, hopefully we already know that this one's not true. The normal curve never crosses the x-axis, right? So it gets down really low, and then it's just kind of a horizontal asymptote, right? If you think of that. So it never crosses the x-axis. So just keep in mind, this is staying above it the whole time. So we know it doesn't cross. Now at 3 and -3 z-score, we've got 99.7% of the data. So there's very little outside of that, but there still is some data. Okay. The normal distribution is a mathematical model of a population distribution. And this is correct. This is not the actual distribution of the population, but this is the model that approximates the population distribution. And this line is defined by an equation. And there's classes you can take that are calculus-based statistics where you can find the actual volume using integrals under the curve, finding the area there. So this is just a model that does a good job of representing the true population distribution. So that one, well, actually, okay, kind of labeling this wrong here. This one is not true, so it's probably our right answer. B is true, so I'm going to cross it out. The total area under the normal curve is always 1. Yes, 100% of your probability falls under that curve. The proportion of observations 2 standard deviations above the mean is the same as a proportion of standard deviations of 2 standard deviations below the mean. I think this is worded awkwardly, but if we've got our 2 standard deviations above and below, we're going to have the same proportion that's more extreme than that. So this area to the left of the lower and above the upper will be equal. And this is just talking about the fact that it's symmetric. And values located on the normal curve are not meant as actual observations. That's true. This is just modeling what we have as an actual distribution. And it's going to come close, but yeah, it could actually be a little bit above with the true population. Okay. Next one is problem 64. This is one I just want to conceptually talk through. It's somewhat of a time-consuming problem, but we've got 2 normally distributed populations, A and B, and we can certainly calculate some z-scores and area under the curve for A and for B separately. And the area under the normal curve is greatest in which scenario? So what we've got are 2 different normal curves going on. This is A and B. So this one's a little wider because the standard deviation. So this is 75. This is 50. And anyways, we can go through and we can figure out the area for all of these. You can see it's going to be somewhat time consuming. The area, so for the first one, area below a value of 25 in population A. Well, if my standard deviation is 12, that means I got 38 and 62. And then this comes down to 26 right here. So 25 is going to be somewhere about right there. And it's going to be that part of the population. So maybe I can just visualize this a little bit. Area above 65 in population A. So here's 74. So which one is it? 65. 65 is going to be somewhere around here. Well, that one's bigger. So between those two, I can see that it's not going to be A. Now, area between 75 and 90 in population B, 75 and 90 is going to be right here. So that looks bigger already. So anyways, if I go through, I can find what the biggest proportion is. Okay. So I think the answer is going to be C on that one, but you guys can confirm that by looking at the other 2. with this problem, we're looking at the least squares regression line. And this is just a reminder of how we find this. So you can create two lists, and this would really be your X and your Y. So what I've got are all the X values, 8, 4, 7, and 5. And all the Y values that correspond right there, 4, 3, 3, and 2. And if I create those lists, I can just do, and we haven't done this one in a while, but I'll give you a second to put those into lists. If you are still putting your data into lists, that's okay. I can repeat this if you guys need to hear it again. But now to find our regression equation, we want to go to stat, over to calc where we were finding one variable stats. We're going to scroll down to number 8, which is the linear regression A plus BX. I'm going to pick my two lists. And when I do that, it gives me my A and B values to plug in. So the normal regression equation, or the standard before we plug in actual coefficients, is that, oops. So now I'm just going to plug in my A and B. So A is 1.2. Hopefully you guys got the same thing. B is 0.3. And I can look for whatever answer has that. Looks like E in this case. So the calculator does the work for us, but we can find that. Another thing just to throw in here, remember you've got your slope is equal to R times the standard deviation of Y over the standard deviation of X. I'm not going over those types of problems. Y bar equals A plus B times X bar. It will go through the average X and average Y value, your regression equation, your regression line. So you might want to find some of those problems where we found it from scratch, and that's a good thing to be looking at. All right, now we're going to jump to another problem. Okay, in this particular problem, I'm not even going to go over because I don't like these answer choices right here, but it is worth it kind of to look at this question, and you can kind of read through it on your own, but I wanted to remind you what the outliers, high leverage points, and influential points are. So if you have a regression right here, or sorry, a scatter plot, let's say that's what you start with, and you've got a point right here, this is obviously an outlier. Okay, it's far above what we'd expect it to have based on where the regression line falls. It would have a high residual, you could say. All right, now it's only influential if it changes the regression line significantly. There's no real cutoff right now for what significant changes are, but let's say that this is what it would be without that. If it changes it to something like this, that would be a significant change. It would be influential and an outlier. All right, now we could have a different situation going on where you've got your data right here, and then you've got this point way out here. This is separated in the X direction, so this is high leverage, this point, but it's not an outlier because it still falls pretty much in line with the trend of the data. High leverage, not an outlier, not influential, we would say. But if this point was moved down and now it's sitting right here, then that would be high leverage, an outlier, and it would be influential because that would be the trend line without that point, and then it probably changes it to something more like this. So influential means it changes your regression equation. Leverage means it has a big change in the X direction. Outlier means it's pretty far off from what we'd expect based on the rest of the data as far as the residuals go. Okay, good review stuff with that. 82, which is the strongest, which indicates the strongest relationship, which has the highest correlation? So for 3 of these, they just straight up give us a correlation. And between those 3, we'd go with this one. It's the furthest from 0. But we have a couple of coefficients of determination, R squared. So we want to figure out what these R values are. If we do the square root of 0.01, we get 0.1. If we do the square root of 0.23, we get 0.48. And what we don't know is if it's positive or negative, but for this problem, that doesn't matter. What matters is that this has the strongest correlation, the strongest relationship between the 2 variables. Now, I should add a caveat to this. It says, we can't know this 100% without seeing the scatter plot, but we'll assume these are all linear. Okay. 92. All right, this is, so we're just looking to explain this situation a little bit. We've got early stages of cancer in this group, advanced stages of cancer in this group, and we've got 2 treatments being tested, or this is observational study. We had treatment A being given and treatment B being given. And what we've got is remissions and deaths. So it's we got a 2-way table that we're kind of looking at with this, but which table correctly shows the aggregation of the data? So we're going to combine this together. So I know that now it doesn't matter if it's early or advanced. I'm going to just combine these. So remissions from A are going to combine together to make 9, and then 7, 11, and 8. So that part isn't too bad. Now we want to figure out the actual remission rate. So it's going to be 9 out of the total. 9 out of 17, or 9 out of 16 means I'm going to have a 0.563, because we can see that's how they put it there, 0.563. And then 11 divided by 19 is going to be 0.579. Again, it's 11 out of the total 19 to give us that. So it looks like A is the answer. Nothing too complicated with that as far as math goes, but we never really combined tables. So this is kind of a new thing, but it's also, it's not a big conceptual jump from anything you've seen before. Okay. '98 is just asking, we want to set up an experiment. We've already seen an observational study that indicates that vitamin C helps you recover from the flu faster. Now we're going to create an experiment. And what are the treatments going to be for this experiment? Since vitamin C is the kind of the explanatory variable, if you will, for this, it's the treatment that we're thinking is going to have some kind of a causal effect on the length of the flu. We are going to administer different amounts of vitamin C, which would be right here. That would be the treatments given to our participants. So the only reason I want to talk about this is just to remind you about some of the terminology we had when we were looking at experimental design. So highly recommended you go through all this stuff to remember that terminology. And there's a lot of stuff in here about stratification when you're looking at sampling versus blocking when you're setting up experiments. So keep in mind there are sometimes different names for the same things based on the context. Okay, if we jump down now to 115. All right, so this is a survey, and here's kind of the key thing. This is the question that was asked: agree or disagree? Since our economy can't sustain itself without a healthy environment, it's important that Congress pass laws to protect the environment. So this is an example, what we would say here, this would be response bias. This is definitely a very biased question to get people to respond a certain way. So you'll notice response bias is not here. They say in this, it was a leading question. This is one type of response bias. But response bias is anything that influences someone's response, like the wording of the question, how you present yourself when you're asking the question, even the question order on the survey can have an effect. So on the test, that if there's any question like this at all, you would see the word response bias, not leading question. So I just wanted to point that out. I'm going to jump down to 128 now. Okay, this one's a fun one. So we've got two dice up here. Let me scroll up just a little bit. There you go. You can see it. The first die has these numbers, and the second one has these. And we want to figure out the probability of getting a sum greater than or equal to 20. Now, we don't have a straight up formula to do this. What we need to do is we need to create the entire sample space. And we can do that when we roll both these die. We could get one of 6 outcomes for the first die: 1, 3, 5, 7, 9, or 11. Okay, we could get any of 6 outcomes here: 2, 4, 8, 10, 11, or 15. And now we just want to create what all the outcomes are. So I'm going to add these together, and this will be really fun to watch me do this. But I'm going to create a table. 3. This is 4 right here. So that's going to be 5, 9, 11, 12, 16. All right, and now I'm going to add 3 to everything. All right, now I'm going to add 5. Now I'll add 7. Nine. And finally 11. Okay, so you'll have to do something like this. We know there are 36 outcomes. 6 times 6 gives us 36 outcomes. And how many of those are 20 or greater? I got 1, 2, 3, 4, 5, 6, and this one right here, 7. So it's 7 out of 36 is the final answer, and you'll see it's in decimal form. So there we go. It's 0.194, which is E. All right. But there's lots of stuff with independent events. These are independent, but are they independent? Are they mutually exclusive? In fact, we have a question coming up. It might be the next one about mutually. No, it's not. It'll come up later. Mutually exclusive. So 135. Which of these are discrete random variables? Remember, discrete means that it can only take on specific values. Continuous means it can take on any value in the range. But discrete can only take on specific values. So if you're talking about enrollment at a state university, that is discrete. You can only have a positive integer there, what we call a natural number, if you guys have heard that before. You can only have 1, 2, 3, 4, just integer values for this. So it's discrete. Outcomes of a loaded die. It's going to still be 1, 2, 3, 4, 5, or 6. You can't get like 2.5. So those are both discrete. The set of all random numbers between 1 and 10, Well, it doesn't say random integers, so all random numbers could be any real number between 1 and 10. So there we go. It looks like only these two are discrete. Just 4 more problems we're going to look through, so not much left to talk about. We've got a random experiment with S equals, and this is maybe something we didn't talk about a whole lot, but this notation right here is for the sample space. And so if you're rolling a die, your sample space is 1, 2, 3, 4, 5, and 6. All right, I feel like we did mention this at one point, but it wasn't a big point of emphasis. So now we're trying to figure out what are mutually exclusive events with B. So if we have, well, I'll just call this one event A. So B has a sample space of C, E, and G. And I don't know what C, E, and G are, but those are some values that it could take on. Event A cannot share any outcomes with B if they're mutually exclusive. So the other options here are A, B, D, and F. As long as it only has those as outcomes and some combination of those 4, then they are mutually exclusive. There's no common outcome between the two. And it looks like all of these right here are legitimate answers. So I'd go with D, all of the above. Okay. This one, okay. Now this is going to seem like a new thing that I'm throwing out here. Technically, this was in the chapter, and we did talk about this, though kind of as an aside. Normally, when we're dealing with random variables and scaling them by doing like, in this case, 3 plus 6x, normally we're dealing with either the mean or the standard deviation, but here we're dealing with the variance. So let's remember something that happens. And this is from the notes in the book itself. If I had the standard deviation of 3 plus 6x, well, the 3 doesn't do anything, but that would be the same as 6 times the standard deviation of x. So let me just erase this real quick. That 3 plus doesn't affect anything. So the standard deviation of 6 times x is going to be 6 times the standard deviation of x. And that's all well and good. But now we're looking at the, oops, not the square root. We're doing this squared, which equals this squared. So that's going to be 36 times the variance. Remember, and I'll just write this in a general way. If I have the standard deviation of c times x, or the variance of this is going to be c squared times standard deviation of x squared. And that is a formula that we introduced. I don't think we ever used it, which is why this seems new. But basically, I can just take the variance of x and I can multiply it by 36. The variance of x given here is 1. So it's just going to be 36 times 1, which gives me 36. I would not put a question like this on the exam tomorrow, but I'm glad that this one's here so we can talk about it. And so the answer is D. Okay. 149. Okay. This is a very quick thing to talk about. If this looks familiar, this is the way that we calculate your binomial PDF by hand. All right, and remember this notation right here is the same as 8 choose 2. And we have a standard form of this. N choose k is equal to the probability raised to the power of k times 1 minus the probability raised to n minus k. And that's on the AP formula sheet. You don't have to have it memorized, but this is basically saying we're calculating a binomial PDF. So I'm gonna get rid of some answer choices here. That's a CDF. This one's a CDF. So it's not going to be either of those. So now I need to figure out if it's 8, choose 2. This is N, and this is I say K. I'll call it X here. So 2 successes out of 8 trials, and right here that first probability 0.3 is the probability of success. So out of 8 trials, I want 2 successes with a 0.3 probability of success, and that's going to be this one right here. Last question to go through is right here. This is maybe one of the most morbid ones that we'll see. The probability that a given 80-year-old person will die in the next year is 0.27. What's the probability that between 10 and 15 inclusive of the 40 80-year-olds will die in the next year? So this is why it's so morbid. We're going to consider a success is one of these 80-year-olds dying. So sorry, Grandma. What we've got is a set number of trials. So N is equal to 40. The probability of a success, 0.27. And we've got a couple of things. We haven't done a question quite like this one, but it really isn't a big stretch from what we do know to do this. We would normally say something like, what's the probability of 15 or less? So that would mean my X value that I'm interested in is 15. And I want a cumulative frequency. So I'd want to do a binomial CDF of 40 trials with a 0.27 success rate. And again, death is a success here, with 15 successes cumulatively, meaning 0 successes, 1, get all those probabilities, add them together, and we get this calculation. But of course, we don't really want to know the probability of 0 through 9. 10 is the first one that we're interested in. So now, and this is kind of the new thing, we haven't done one quite like this yet. Here's where I would want to subtract another cumulative binomial probability. Still 40 trials, still a 0.27 probability of success, but now I want to go up to 9. And what this would do is it would subtract away all the probabilities of 0 through 9. So I'm left with only the probabilities of 10 through 15. So we can calculate that real quick. And I got 0.6191 when I did that. Okay. So of these 159 questions, there's a good amount that I'm just gonna, I don't know, maybe about 15 of them that I just say skip these completely. And maybe more than that before I post it. But anyways, so there's gonna be a number of these you can just skip completely. The rest of them, skim through. It's a lot, it's a tall ask, I know, but go through this as much as you can. And if there's any that you just look at and you're immediately confused on, just put a star next to it. Come to class tomorrow. You can have a list of, however many questions and say, I'm not going to go through all 150, but if you have a list of a few questions, we can go through and we can figure out what's going on. The quiz questions tomorrow are not going to be exact duplicates of this. They might not even look like a lot of these, but they will look like questions you've seen on your tests leading up to now, and maybe similar to these in some ways. So if you can go through this, you should be fine. Again, if you're satisfied with your grade, you can't hurt yourself tomorrow. So if you're really trying to bring your grade up, this is where you need to spend a lot of time studying tonight. All right, I've talked enough. That's all I've got for today. Hopefully this was helpful. This will be posted very soon, and I will see you guys tomorrow.